All right, well, welcome back. We're now working on section 5.1. And 5.1, again, catch the pattern of this modern algebra class as we go through the chapters and stuff. And again, I mentioned to you guys before about this pattern of from chapter 1 and 2. So you got to master chapters 1 and 2. And because most students that actually ended up bombing this class, they did not catch the pattern in chapter 1 and 2, and they get lost through the rest of them. Of course, we continue to add patterns and structure to these things, but the pattern still holds. Take a look at chapter 5.1, and you're going to see that pattern once again. So chapter 5 is going to be equivalent to chapter 2. Let's take a look. Chapter 5.1, Congruence in F adjoint X and Congruence Classes. Definition. Let F be a field, and f of x, g of x, p of x be elements of F adjoint X, with p of x being a non-zero polynomial. Then f of x is congruent to g of x modulo p of x, written in the form f of x with the equivalence being 3 little equal to guys there. F of x is congruent to g of x mod p of x, provided that p of x divides f of x minus g of x. So it's the same thing as what we did with integers in the modulo n world. A was congruent to b mod n, where a and b and n were integers, provided that n was not 0 and n divides a minus b. Here, p of x divides f of x minus g of x. Same concept here. So let me throw an example your way. In Q adjoint X, remember Q was the symbol for rational numbers, fractions, that's a field. In Q adjoint X, x squared plus 2x plus 5 is congruent to x plus 11 mod x plus 3. Why? Well, kind of walk this out as a proof. Well, what's the definition of congruence modulo x minus 3? This means that x plus 3. Mod x plus 3. This means that x plus 3 has to divide the f of x squared plus 2x plus 5 minus x plus 11. So x squared plus 2x plus 5 minus x plus 11. So when you distribute the negative and combine like terms, you'll get that x plus 3 must divide x squared plus x minus 6. I did go ahead and skip a step in terms of my canceling and stuff, but you'll also notice that since x squared plus x minus 6 is equal to x plus 3 times x minus 2, x plus 3 really does divide x squared plus x minus 6. So, yes, this is a true equivalence class. X squared plus 2x plus 5 is congruent to x plus 11 mod x plus 3. So, theorem. 5.1 says this. Let F be a field. And p of x a non-zero, because you can't divide by 0, a non-zero polynomial in F adjoint x. Then the relation of congruence modulo p of x is reflexive, symmetric, and transitive. Reflexive reminds you of what it means to be reflexive from a congruence class perspective. You've got to be basically equivalent to yourself. So f of x is congruent to f of x mod p of x for all f of x in f adjoint x. Now, why is that true? Well, what's the definition of congruence modulo p? So f is congruent to f mod p of x means that p of x has to divide f of x minus f of x. Well, last time I checked, f of x minus f of x is 0, and any non-zero polynomial divides into 0. So that's trivial. Symmetric. Well, if A is equivalent to B, then B has to be equivalent right back to A. That's only fair. That's called the symmetric property. If f of x is congruent to g of x mod p of x, then g of x is congruent to f of x mod p of x. Now, why is that? Well, here's the deal. The definition of congruence modulo p of x means that f is congruent to g mod p means that p of x divides f of x minus g of x. Well, if p of x divides f of x minus g of x, p of x is going to divide -1 times f of x minus g of x. Well, -1 times f of x minus g of x is actually g of x minus f of x. So since p of x divides g of x minus f of x, therefore g of x is going to f of x mod p. And you're done. Very similar how you walk through it. And of course, to make a congruence class, you have to have the transitive property, which means this. If f is congruent to g mod p of x, and g of x is congruent to h of x mod p of x, then f of x is going to be congruent to h of x mod p of x. And you basically just follow through by a bunch of divides and definition divides if you want equations. So f congruent to g mod p means that p of x divides f of x minus g of x. And given that g is congruent to h mod p of x means that p of x divides g of x minus h of x. So you can take these equations when you use the definition divides and pretty much just add them together. So the minus g and the plus g will cancel, and you'll be left with f of x minus h of x is equal to p of x times somebody plus p of x times somebody else. You can factor out your p of x, which means that p of x divides f of x minus h of x, which means f is congruent to h of x mod p of x. This also means that the congruence modulo p of x forms an equivalence class. And when you talk about these equivalence classes, they have a ring structure. So we're creating new rings. But you've kind of seen these rings before. But to create a ring, you've got to talk about the idea of addition and subtraction. You've got to have your properties here. So Theorem 5.2 says this: let f be a field, and p of x a non-zero polynomial in f adjoint x. If f of x is congruent to g of x mod p of x, and h of x is congruent to k of x mod p of x, then f of x plus h of x is congruent to g of x plus k of x mod p of x, and to f of x times h of x is congruent to g of x times k of x mod p of x. You can add congruence classes and still be congruent mod p of x. You can multiply congruence classes and still modulo p of x still be a congruence class. So you can add them and you can multiply them. You have ring structure. And because we have ring structure, we're going to have to define what these equivalence classes are going to look like. And notice the notation. Catch a pattern on this class. Again, where most students have messed this class up in the past, especially when you teach summer school, you get some folks that didn't do well in the regular semester. And I can tell you, every one of them have come to me and said, this makes so much sense now because you're actually explaining the pattern that I never got before. Pay attention to the pattern. Look at the pattern. Definition. It says this: let f be a field, and f of x and p of x elements of f adjoint x with p of x non-zero. The congruence class or residue class. Now, I put here, you are familiar with congruence class, remember chapter 2, but I'm also using the big word, another big word called residue class. So when you get to graduate school, they're going to start talking about these residue classes and things like that. Don't worry, residue classes, congruent classes, same thing, just a different name for it. So congruence class or residue class of f of x modulo p of x is denoted by, interesting, pointy bracket f of x, and consists of all polynomials in f adjoint x that are congruent to f of x modulo p of x. That is, and so here's my little set notation thing here. The congruence class, and this is how you read it, the congruence class of f of x is equal to all the g of x polynomials such that g of x is an element of f adjoint x, that's the first property, and the second property, g of x is actually congruent to f of x modulo p of x. So the p of x will be given because that's what you're modding out by. So this is all the polynomials such that when I subtract off f of x, p of x divides it. That's what this congruence class is. There's a pattern. So let's take a look. Example, consider the equivalence class 2x plus 1 in R being the real numbers, that's got to have a field adjoint x. So polynomials where the coefficients come from the reals. And we're going to do modulo x squared plus 1. So this is my equivalence class mod x squared plus 1. So therefore, the equivalence class of 2x plus 1 is equal to the polynomials g of x, elements of f adjoint x, such that g of x is congruent to 2x plus 1 mod the x squared plus 1, which means, by definition, that this equivalence class 2x plus 1 are all the polynomials such that x squared plus 1 divides these polynomials g of x minus 2x plus 1. So this is all polynomials g of x and f adjoint x. When I subtract 2x plus 1, the x squared plus 1 divides into it evenly. Yes, there's an infinite number of these polynomials in 2x plus 1, But also notice that 2x plus 1 is in the equivalence class of 2x plus 1. And again, this is something I talked about before when we talked about Z mod n stuff. You got to be in your own equivalence class. That's only logic and the way God meant it in terms of equivalence classes. You must be in your own equivalence class. And the reason for that is, well, 2x plus 1 is in the equivalence class of 2x plus 1 because 2x plus 1 minus 2x plus 1 is 0, and any polynomial divides into 0, as long as the polynomial originally was non-zero, so you don't have to worry about a 0 for 0 case. So you're always in your own equivalence class. Remember that. But it's all the other polynomials that when I subtract off 2x plus 1, this x squared plus 1 will actually divide into it. That's what makes it. So you got this infinite set that's being grouped together. That's what these equivalence classes are. So let's get a little more interesting with this particular material. Here we go. One more theorem, and then we'll get some examples here. Theorem 5.3 says this. If, well, given, sorry, f of x is congruent to g of x mod p of x, if and only if the equivalence class of f is equal to the equivalence class of g. And f of x, g of x, and p of x are all polynomials in f adjoint x, where f's a field and p of x is a non-zero polynomial. Because you can't mod out by a zero polynomial. You can't divide by 0, so it's always got to be at least a non-zero polynomial here. But, so when f of x is going to g of x mod p of x, f of x and g of x are going to be in the same equivalence classes. So, their corollary, 5.4 off that guy, is this. Two congruence classes modulo p of x are either disjoint, they have nothing in common, or they're going to be identical. They'll be equal to each other. Your big one is corollary 5.5. Comes from theorem 5.3, but it says this. Let f be a field, and p of x a polynomial in f adjoint x of degree n. Consider the congruence modulo p of x. 1. If f of x is an element of f adjoint x, and r of x is the remainder when f of x is divided by p of x, then the congruence class of f is equal to the congruence class of r of x, the remainder polynomials. Just like we did in z mod n. Z mod 5. What were the equivalence classes in z mod 5? 0, 1, 2, 3, 4. Why? Because when you divide by 5, the only remainders you can get are 0, 1, 2, 3, 4. When you divide by, take f of x and divide by p of x, it's equivalent to what its remainder going to be. The key is going to be the remainders when you're dividing by p of x to create equivalence classes. So they try to discuss this in a very vague way. So here it is. This is part 2 of corollary 5.5, what Dr. Hungerford stated. Let S be the set consisting of the zero polynomial and all polynomials of less than n in f adjoint x. So remember, p of x has degree n. So any polynomial of less than n in f adjoint x. Every congruence class modulo p of x is the class of some polynomial s in S, and the congruence classes of different polynomials in S are distinct. Okay? So we're going to create this idea of congruence classes, and it's all the possibilities of remainders you can get when you divide by p of x. This set S is denoted by, and here's the notation for it, f adjoint x, that's your polynomial ring. For mod, we're going to put a little slash for it. It really remembers that divide by a little parentheses around it, p of x. That's my notation for the new ring that we got. And yes, it's going to make a ring, these congruence classes. So, turn the page over here, and I've got some examples for you guys. So, before I jump through all my examples, let's talk about one at a time. So, I'll use my little piece of paper here. Examples. Q adjoined x, modded out by 4/3 x cubed plus 2x squared minus 7x minus 1/5. Now remember, Q are the rationals, fractions, fractional integer over integer. Joined x, polynomials where the coefficients are fractions, rational numbers, integers divided by integers. So here's a classic one. Now, when you divide by 4/3 x cubed plus 2x squared minus 7x minus 1/5, I don't care about the coefficients. Are you dividing by x cubed? When you divide by x cubed, what's the biggest degree polynomial you can have for a remainder? Well, when you divide by x cubed, the biggest thing you can have is an x squared for a remainder. And so I'm going to call it, this is a general form, ax squared plus bx plus c, where a, b, and c can be any rational number. So I got infinite number of rational numbers for A, infinite number of rational numbers for B, and infinite number of rational numbers for C. So this is an infinite number of congruence classes. But they're going to be in the form of ax squared plus bx plus c. Quadratic looking type of congruence classes because you're modding out by a cubic. And so when you divide by x cubed, the biggest thing you can get is a x squared for the remainder. Catch a pattern. So let's talk about finite fields. So here we go. Z5 adjoin x modded out by equivalence class 3 x squared plus equivalence class that's just equivalence class 1 times x. That'll be just 1 times x. Sorry about that. Don't put the pointed brackets around the x. Plus 4. Okay, but honestly, we don't write the pointed brackets when we're talking about polynomials, even in Z5 adjoint x. It's understood that these coefficients have to be elements of Z5, which is 0 through 4. 3x squared plus x plus 4. When you divide by an x squared, that's a quadratic, the highest degree, that's a degree 2, so that the remainder has to be a degree 1 less than that, a degree 1 polynomial. Degree 1 is the famous ax plus b. Degree 2 was ax squared plus bx plus c. A degree 3 would be ax cubed plus bx squared plus cx plus d. So you're looking for these patterns of 1 less degree, and the coefficient is going to be arbitrary when it comes from the field. So when you divide by x squared, you get linear, ax plus b, where a and b have to come from the field Z5. So how many equivalence classes are there going to be? Well, I've got 5 choices for a, 0, 1, 2, 3, 4 equivalence class. I got 5 choices for b, 0, 1, 2, 3, 4. That's what makes up Z5. And 5 times 5 is 25 congruence classes. So this is actually going to be a finite amount of congruence classes. These guys will be 25 of these guys. Okay, keep going. So I wonder we can actually write down and stuff. Z3 adjoin x modded out by 2x squared plus x plus 1. All right, so in Z3, you're allowed to have numbers of 0, 1, and 2. So this is all my coefficients have to be a positive 0, positive 1, and a positive 2. So this is 2x squared plus x plus 1, because we don't typically put the pointed brackets around my polynomial. We just have to tell you where these guys are coming from. Z3 adjoin x modded out by 2x squared plus x plus 1. Now, I don't pay attention to the field yet. I pay attention to the degree. This is a degree 2. 1 less than degree 2 is degree 1. Degree 1 is linear. Linear is ax plus b, where a and b come from Z3. They have to come from the field. So I got 3 choices for a and 3 choices for b. 3 by 3, product, the multiplication principle here. 3 times 3 is 9. There'll be 9 equivalence classes. Let's write them all down. So 9 equivalence classes, and there's a pattern to this. I make a equal to 0, and I run the gamut on b. B is going to be either, remember, Z3, you've got a choice of equivalence class 0, 1, and 2. So A is 0, B can be 0, 1, and 2. So 0x plus 0 is 0. 0x plus 1 is 1. 0x plus 2 is equivalence class 2. Now I'm going to bump it up. A could be equal to 1. If A is 1, that'll be 1x, and then run the gamut on B, 0, 1, 2. So that'll be 1x, x plus 1, and x plus 2. And the last thing, A could be 2. So that'd be 2x, 2x plus 1, and 2x plus 2. And then those 3 by 3 is, I got 9 equivalence classes. These are actually all the equivalence classes of Z3 adjoined x modded out by x squared, 2x squared plus x plus 1. So you can actually, again, write these guys down. So that's the idea behind these guys. Now, to create the ring structure, we're going to move on into section 5.2, and that'll be on our next set of videos here. But that's the key, is I want you to really focus in on this one, especially with these finite fields. When you got rationals or reals, there's going to be infinite number of equivalence classes here. But again, regardless, You see what you're dividing by in terms of degree, and remember your equivalence class is always a degree 1 less than that. The equivalence classes are the remainders polynomials when you divide by whatever the p of x is given to you. That's the key to this stuff. So section 5.1 is very, very similar to what we did in chapter 2 with z mod n, but now we're doing f adjoint x modded out by polynomial p of x.